Now that we have stress defined as our force per unit area and our strain defined as our deformation per unit length, we can create something called the stress strain curve, which is going to be unique to our material, and it's not going to be dependent upon the geometry of our specimen. Now note in our stress strain curve that our stress is normalized per area and our strain is normalized per length. All our geometric dependence is now removed. The generation of a stress strain curve is done via tensile testing, and you can click this link to watch a video of a tensile test. For low carbon steels, we have the following stress strain diagram. On our y-axis we have our stress, and on our x-axis we have our strain. Our strain is reported as a percent. Now there are some very unique key features to our stress strain diagram that we have to talk about. The first is our yield strength of our material. Our yield strength is denoted as sigma sub y. Now the yield strength corresponds to the yield stress of our material. And for ductile materials, we do a 2% offset and draw a line that is parallel to our linear line that goes from our origin up to our yield strength. Now our yield strength is going to be our design point within our system. We never want to exceed our yield strength, for we'll talk about what happens if we do. Below our yield strength, we have linear behavior with our material. This region is known as our linear elastic region. Linear indicates that our line behaves linearly, and elastic means our material is behaving elastically. That is, we can apply a load, then remove the load, and our material will return to its original size and shape. Sigma U is our ultimate strength of the material. This is the maximum strength that our material can withstand. Now note that sigma U exists when we have about a 20% strain within our system. We do not ever want to take this as a design point, for we had major deformation within our system. Within our linear region, we have to talk about two unique features. The first is our proportional limit. And the proportional limit marks a transition from linear to nonlinear behavior. And this point is going to exist below our elastic limit. Now, a proportional limit is going to be very important because below our proportional limit, we can easily model the behavior of our material because we have a straight line. Now, beyond there, we do not have an equation to model the behavior of our material, and we have to rely on our stress strain curve to determine our deformation versus our applied load. Now, our elastic limit is just above our proportional limit, and the elastic limit is where, if we exceed, our material will not return to its original shape. But if we are below our elastic limit, our material will return to its original size and shape after loading. Our elastic limit is synonymous with our yield point, which corresponds to our yield stress and yield strength. When we are beneath the proportional limit, our stress-strain relationship is given by Hooke's law, also known as the modulus of elasticity and also known as Young's modulus. Hooke's law states that our modulus of elasticity, capital E, is equal to our stress sigma per our strain epsilon. That is, we have our rise over our run. E is simply the slope of the line in our linear elastic region from the stress strain diagram. E is a material property that does not depend upon the size or shape of our material, and E differs for a variety of materials. We will talk about this momentarily. Similar to our stress strain diagram, we can have a shear stress shear strain diagram, which we will cover shortly. In our shear stress shear strain diagram, we have G, which is our shear modulus, or our modulus of rigidity, is equal to our shear stress per our shear strain, which we'll introduce momentarily. Now, once again, G is a material property that is not dependent upon size or shape. Now, some common values for our elastic and shear modulus are as follows. For structural steel, our elastic modulus is typically on the order of 200 gigapascal, and our shear modulus is typically on the order of 76 gigapascal. For aluminum alloys, our elastic modulus is typically around 73 gigapascal, and our shear modulus is typically around 28 gigapascals. Now, each material is going to have a unique modulus of elasticity and a unique shear modulus. You have to look this up for the material. For the alloy, as well as a manufacturing process, changes of the material property. Now, as noted, the R modulus of elasticity quantifies the resistance of our material to deform via axial loading. A material with a high modulus of elasticity can withstand a high stress before eliciting a certain amount of deformation. Our shear modulus, or modulus of rigidity, is the resistance to shearing. A material with a high modulus of rigidity can withstand a very large shear stress before eliciting a certain amount of deformation. Our stress strain diagram for aluminum alloys is as follows. We note that aluminum alloys exhibit a linear elastic region that is below our yield stress. Now, contrary to our low carbon steels, there is no yield. That is, as we go from our yield stress, we increase nonlinearly to our ultimate stress, where right after our material ruptures. Previously, we introduced shear strain. Our average shear strain of an element is given as follows. Our average shear strain, which is known as gamma average, is equal to our deformation due to shear per our initial length, and this is shown in the diagram below. If we consider our box pinned at our origin, as noted in diagram A, with an applied load F, we would note F sub x is going to cause a shearing across the top of the box, and F sub y is going to cause a shearing across the right face of the box. This will cause a deformation delta with respect to our x and y axes, where a box is going to deform some angle phi. We can say our average shear strain is our delta due to our shear per our initial length, and for small angles this is approximately equal to tan phi. Let us look at an example of shear strain. We have a rectangular block material that is bonded to two horizontal rigid plates. Our lower plate is fixed to the ground while our upper plate is subjected to a horizontal force P. P is providing shear to our system. Knowing our upper force moves our upper plate 0.0400 centimeters and our material has a height of 2.0000 centimeters, we want to determine the average shearing strain, gamma xy. Xy just indicates that the plane we are looking at. For us to determine our average shearing strain, we recognize that our average shearing strain is equal to our deformation per the height of the body. That is, we're going to take our deformation of 0.0400 centimeters per the height of our body, 2.0000 centimeters. And our average shear strain is 0.0200. We note that this is dimensionless. And if we calculate our angle phi, this is approximately equal to 1.15 degrees.